Welcome to the Sky Commander Flight Brief. It's your mission-ready podcast for drone pilot training and aerial insights across Canada.
From Transport Canada rules to real-world drone ops, we break it down, take you higher, and help you earn your wings. Because here at skycommander.ca, we don't just fly.
It hints there's more to it. It's a masterclass, a deeper level, maybe a philosophy or a community focus, perhaps.
It's definitely intriguing, sets them apart from just, a basic tips show. Skycommander.ca is the obvious next step. Precisely. If you're thinking about flying a drone in Canada, boom, this content is aimed right at you.
Powered by skycommander.ca.
The elite podcast for Canada's drone pilot. Okay, let's get started. This is the place where we take all that dense industry source material, the field reports, the training manuals, the best practices, and we really boil it down to the critical, actionable knowledge that you need.
And today, we are strapping in for a pretty intense one. We're going deep into one of the most technical and, I'd say, critical fields in modern infrastructure.
We're talking about drone tower inspections.
Exactly. And look, we're not just talking about cell towers, though, of course, those are a huge part of it. Mm-hmm. We're talking about the entire landscape of communications assets.
You mean like the big, stout water towers, those massive lattice structures that look like giant erector sets?
Right, and the simple monopoles you see along every highway. The sheer volume of these things and their geometric complexity, it's just staggering. And they are really the circulatory system of our digital lives.
So our mission today is to unpack that whole workflow. We're not just looking at how a drone flies near a tower. I mean, honestly, anyone can go buy a drone today and get it within 50 feet of a structure. That's not the point.
No, not at all.
We need to understand what separates a professional, a regulated inspector, from a hobbyist. We're talking about the critical safety discipline, the deep regulatory mastery, and just the sheer technological skill you need to deliver useful, defensible evidence to a client.
And that phrase right there, defensible evidence, that really sets the stakes, doesn't it? We have to contrast this new way with the old way.
The traditional approach.
Yeah, think about it. You've got trained rigging technicians using rope access. It is incredibly slow. It can take a whole day just to rig one complex tower.
A whole day?
It's monumentally expensive because you have this highly specialized labor. And most critically, it is inherently risky. Even for people with thousands of hours of training, it's just dangerous. The sources make it so clear that drones aren't just a convenience. They're an economic and a safety imperative.
It's not just an upgrade, it's a complete shift. I mean, a magnitude shift in safety, speed, and cost. We're watching this industry transform in real time. And the core driver, the thing that convinced the entire telecom sector to invest, it all comes down to one thing.
Eliminating human risk.
Right. It's that simple.
It is.
I love that the industry, which, can be a bit slow to adopt new tech sometimes, has moved so fast on this. It's gone from seeing the drone as a gimmick to accepting it as a primary risk mitigation tool.
It's a tool that pays for itself just by reducing liability.
Yeah.
There was a quote in the sources that just sums it up perfectly.
Oh, I know the one you mean.
They can't fall off the tower if you don't send them up.
Exactly. It's that simple.
That phrase should be etched into the side of every ground control station. I mean, when you look at the business case, avoiding human risk is the ultimate game changer. You are removing the single greatest variable and risk factor in tower maintenance.
Which is the climber themselves.
The physical vulnerability of that highly specialized climber. Think about the environment they're in. They're working at high altitude, on exposed steel, often with unpredictable wind, unexpected electrical induction, just sheer human fatigue. Any technology that takes the human operator out of that immediate danger zone, it justifies its own existence right there.
And once you've secured the safety side, the economic benefits just start piling up. The efficiency gains they're truly staggering when you look at the numbers.
Okay, let's look at those numbers because they're wild. Traditionally, you have a 2 or 3 person rigging crew. They're doing a physical, hands-on inspection. They might inspect 1, maybe 2 towers in a very good day.
And that includes everything, right? Driving there, rigging up.
Everything. Mobilization, rigging the safety lines, the actual climb, the physical inspection, de-rigging, then driving to the next site. It's so labor-intensive, so slow.
Okay, so that's the baseline. What's the drone comparison?
It paints a totally different picture. A single drone operator using modern autonomous flight planning, and we'll get into the details of that automation, can get a full data capture of up to 9 assets.
9 in one day?
9 assets.
Oh, day.
A single pilot. So think about that ratio. You go from maybe 2 assets per specialized rigging team, to potentially 9 assets for a single drone pilot.
That's a massive shift in scale.
It completely changes the cost per asset. It dramatically increases the speed of preventative maintenance across an entire network. And this is key, it frees up those highly skilled riggers to do what only a human can do.
The actual repairs.
The actual repair work, exactly.
So the economic benefit is huge just in labor hours, but the sources really emphasize that the data you get from the drone adds value way beyond just avoiding a climb.
Oh, absolutely. What's fascinating is the data's longevity and its measurability.
Yeah.
In the past, a rigger writes a report, right, based on what they saw, maybe with a few photos.
Just static pictures.
And that information has no real context, and it's outdated almost immediately. With the modern drone workflow, you're capturing hundreds, maybe thousands of highly overlapped images, and that data gets processed into a textured, dimensionally accurate 3D model, a digital twin of the asset.
Which means the information is persistent. It doesn't just go away.
Precisely. That 3D model lets an engineer or an asset manager or a contractor review the site again and again without having to send somebody there. An engineer can zoom into a specific bolt, check the angle of an antenna mount, measure the distance between 2 points, years after the drone flew, all from their desktop.
That is the real return on investment, that persistent, measurable data asset.
It elevates the data from just a simple inspection report to a permanent record that can inform decisions way into the future.
And that leads to this other huge source of value the sources mentioned, which is pre-site planning.
Yes, this is huge for big capital projects. Clients and contractors are using these high-res 3D models to understand what a site requires before they send an expensive crew out there.
So they can avoid that classic problem of getting to a remote site and realizing you brought the wrong wrench.
That's the exact logistical nightmare they're solving. With the digital twin, they can check access routes, see how steep the terrain is, confirm the exact length of fiber they need, or even figure out if a crane can get to the base.
And that's critical, because one failed mobilization, sending a whole crew out there just to find out they're missing one specific bracket.
It can cost days of labor and thousands of dollars. Using the 3D model upfront just saves all that capital.
That remobilization cost, which is a huge hidden expense in traditional tower work, it's just gone.
Completely gone. I mean, think about the labor cost. You have a team of 4 specialized techs. They travel for 6 hours. Then they have to turn around because one measurement was off. You've just lost 2 days of productive work, plus fuel, plus transport. The drone data just mitigates that risk entirely.
Plus, we're seeing companies realize they've essentially created a new asset every time they do an inspection. That digital twin starts to open up revenue streams that have nothing to do with maintenance.
It's a classic case of turning a maintenance cost into an asset management tool. They have this incredibly precise model of the tower, and they start asking, okay, what else can this do for us? One source talked about businesses using the models to precisely assess and sell real estate space that's available on their towers.
How does that work? How does a 3D model sell tower real estate?
Well, imagine a new 5G provider wants to install some new equipment. Historically, that meant an expensive preliminary site survey climb just to measure a strut or check the loading.
Just to see if their stuff will fit.
Exactly. Now, the engineer just pulls up the digital twin. They can pull the dimensions directly from the model. They can calculate exactly where new equipment will fit, confirm the structural loading on specific points, even model the wind loading of new antennas, all without sending a human up a tower with a tape measure.
It just speeds up the whole process.
Dramatically.
Yeah.
It accelerates lease agreements and speeds up network expansion.
That is brilliant. Okay, let's talk about the really extreme environments, because the source material brought up the challenge of truly remote sites. This isn't just a marginal gain in efficiency then, it's the only way.
This is where we get to the absolute limit of operational feasibility. A lot of crucial communications assets, especially the ones that provide lifeline connectivity for rural or isolated communities. The sources use examples from New Zealand, like Department of Conservation sites or remote offshore islands. These places are intensely challenging to access.
Yeah, you're not just parking a truck and walking 10 feet to the base.
Not even close. These sites often require helicopters or specialized boats just to get people and equipment there. So if your traditional inspection takes half a day to rig and climb, and you had to charter a helicopter for the whole day,
the cost must be astronomical.
It is. But if a single drone operator can fly in, get a complete high-resolution data capture in, say, 30 to 45 minutes on one battery, that efficiency becomes the only practical and affordable way to maintain that infrastructure.
So in those cases, the drone isn't just replacing a human, it's enabling an inspection that probably wouldn't get done otherwise.
Precisely. Or at least not done nearly often enough. It allows for preventative maintenance cycles that were just economically impossible before. It makes a whole network in those remote areas much more resilient.
Okay, so let's shift from the why, the huge business value, to the how, the operational reality. This isn't just launching a drone and hoping for the best. It's a highly structured workflow that starts the second that inspector's truck pulls up.
The professional discipline starts on the ground, absolutely, long before the motors even spin up.
The first thing is what the sources call the arrival and site scan. It starts with parking the vehicle correctly, then walking the perimeter. The pilot needs to identify every potential hazard. We're talking subtle power lines, trees that could get in the way of a takeoff path.
Loose debris on the ground, and most importantly, mapping out the location of all the guy wires.
That initial meticulous visual scan is just non-negotiable risk mitigation.
It is. And then you establish the safety zones. The sources boil this down to two key concepts, the TOLZ and the safe box.
Let's start with the TLZ, the takeoff and landing zone. Why is the placement so strategic?
The TLZ has to be chosen very carefully. It has to be clear of obstructions, never directly under the tower. You don't want to be under falling debris or intense RF reflection. And ideally, you want it slightly upwind.
Upwind? Why upwind?
It's a safety protocol. In case of an unexpected rapid descent or a battery failure, the wind will tend to push the aircraft away from the tower, not into it. And you have to mark out a mandatory 10 to 15 meter safety bubble around that zone with cones or tape.
And the safe box, that's your escape plan. How is that defined?
The safe box is a pre-selected clear air hover point. It's usually 30 to 50 meters away from the tower at a safe altitude, and it's designated as the drone's default recovery zone.
So if things go wrong...
If the operator hits a control link glitch or sudden wind shear or a compass anomaly from all the steel, the first action is always the same. Stop all autonomous motion, command the aircraft to back out to the safe box, stabilize everything, and then decide if the mission can continue. It prevents panic.
So once that ground safety is set, the real tech kicks in, the autonomous flight workflow. The sources gave some great examples from systems like Hammer missions, showing how pilots move from manual flight to full automation without relying on, say, Google Maps.
And that's a critical technical detail. Relying only on satellite imagery for flight planning near a tower is dangerous. Maps can have real-world positional errors of several meters, and a 1-meter error is a crash when you're flying 8 meters from a $500,000 antenna.
So if you can't trust the map to tell you where the tower is, how do you get centimeter-level accuracy for the flight path?
But professional workflow uses the drone itself to calibrate the mission in real time. The operator flies the drone manually near the tower, gets a precise visual on the tower's vertical center line, and then taps a button on the controller, like the C2 button, which marks the exact 3D coordinates of that center point in the software.
So the drone becomes its own survey tool for a second.
Precisely. Once that true center is marked, the operator can fly the drone away to a safe distance, or even land it, and then apply incredibly accurate, real-world distances to the mission. They can tell it, execute an 8-meter orbit around this point, completely overriding any bad GPS data from a map.
And that also lets you adjust for obstacles you see when you get there, like a tree line that wasn't on the map.
Exactly. You can adjust the whole flight envelope on the fly to make sure it's safe.
That detailed flight planning also has to account for the shape of the asset, right? You wouldn't scan a wide water tower the same way you'd scan a super thin lattice tower.
No, you need versatility in the software. The professional software can switch between circles mode, which does a breadth-first scan, multiple orbits at different heights, great for a wide water tower, and an up and down mode, which is more of a height-first vertical ladder scan. That's more efficient for a typical narrow cell tower.
Speaking of efficiency, let's talk about what it takes to create that high-quality 3D digital twin. We know snapping a few pictures isn't enough. There's a recipe for good photogrammetry.
Right. If the deliverable is that high-res 3D model, the operator has to master image overlap. The default in a lot of consumer drone programs might be, 20 or 30% overlap.
Which is fine for a panorama photo, I guess.
Exactly. But for high-quality 3D geometry, the operator needs to manually crank that up to 70, even 80% overlap, both forward and sideways.
And why is that high overlap so necessary for the 3D model?
Photogrammetry software works by finding shared visual features across multiple images. If there isn't enough shared data, if the overlap is too low, the software can't triangulate the position of a feature in 3D space. High overlap just ensures there's enough data for the software to accurately reconstruct every bolt head, every strut.
And then there's that really counterintuitive problem you mentioned, which is the sky itself being a saboteur.
It's one of the weirdest bits of wisdom in this field. You'd think you want a nice, clear, high-angle shot. But the photogrammetry software gets really confused if it sees big patches of uniform blue sky or the horizon line.
Why would a clear sky confuse a machine?
Because the sky is just a uniform, textureless background. The software relies on texture and unique visual points to figure out scale and depth. If it sees a big area of just one color, it can't anchor those points. The 3D model comes out all corrupted and messy. You get stretched geometry, floating bits. It's useless.
So what's the fix?
The pilot has to maintain a low oblique angle on the drone's gimbal, always pointing down slightly. The goal is to keep the images devoid of any patches of sky or horizon by keeping the ground or the tower itself in the frame.
That's a great example of that specialized knowledge. Now, for some tasks, the human element is minimized even more when you use highly autonomous systems, like the Skydio drone. The sources said it has a really low barrier to training.
The Skydio 2 Plus Enterprise is a totally different paradigm. It moves beyond just simple obstacle avoidance and into obstacle navigation. It uses multiple visual sensors and advanced computer vision to build a detailed, real-time 3D mesh of the tower as it flies.
So it's actively mapping its own environment second by second, not just following a pre-programmed path.
Exactly. It creates a digital twin of its immediate surroundings in real time. This lets it develop its own safe flight path dynamically. The sources say it can dance around power lines and avoid objects as thin as 15 millimeters.
So the pilot's job changes.
Completely. You go from being a manual stick operator, constantly managing the proximity to the steel, to basically babysitting the drone. You're focused on the camera feed and overall air safety, not constant micro-corrections.
That must be crucial when you're dealing with something as complex as a lattice structure. I mean, trying to manually fly in and out of those gaps seems insane.
It would be reckless operation, absolutely.
Yeah.
The Skydio's ability to safely navigate through the lattice is incredible. It's necessary for inspecting the internal joints and legs that you just can't see from the outside.
But even with all that efficiency, you're still constrained by battery life. A single battery might capture a whole tower, but what about missions that need more than one?
It's a core part of the risk assessment. The real risk comes during a battery change. Say the drone runs out of juice on the far side of the tower. The pilot brings it back, swaps the battery, and relaunches.
Okay.
But now, the drone's resumed flight path has to account for that whole 3D structure on its way back to where it left off. The system has to use its own map of the tower to safely navigate through all the struts and antennas to get back to work.
So the resume point isn't just a GPS coordinate, it's a whole 3D trajectory.
Exactly. It's making sure getting back to work is as safe as the work itself.
And once you've captured all this data, we're talking gigabytes of images, you have the final challenge of actually uploading it.
Yeah, this is a real choke point in the workflow. While real-time upload is technically possible, pros almost always wait until they get back to base.
Even if they're sitting right next to the cell tower they just scanned.
Yes. It's a bandwidth problem. They're capturing gigabytes of data. 30, 40 gigabytes for one tower is not uncommon. Trying to upload that over a remote mobile connection would take hours. It would negate the whole time saving of the drone capture.
So the workflow is capture fast on site, then deal with the data back at the office.
Capture fast, dump it onto a rugged hard drive, and process it back at the office where you have high-speed broadband. It's the only way that makes sense.
Okay, let's get into the gotchas. The invisible but really dangerous things that separate a professional from someone who's just going to crash their drone. This is where we move from the physics of flying to the invisible energy and legal boundaries.
This is critical stuff. I like the analogy in the sources.
The porcupine. Picture the tower as a porcupine, antennas are the quills, guy wires are the invisible trip lines, your drone is a moth.
That really grounds you in the reality of the hazard. And the threats fall into two main categories. The invisible energy traps, which is RF, and the regulatory traps, which is compliance.
Let's start with RF safety. Respect the field. What is RF and why is it so dangerous near a tower?
RF is radio frequency. It's the electromagnetic fields coming from the transmitting antennas. It's invisible energy, and at high doses, it poses two serious threats. The first is to people. It can heat human tissue. But for the drone, the critical threat is electromagnetic interference. It can disrupt the control links, the GPS, and especially the compass.
And the power of that RF field isn't uniform, right? It depends on the antenna.
Yes, and understanding the antenna geometry is non-negotiable. This is where that flashlight versus laser pointer analogy comes in.
Okay, explain that.
A standard panel or sector antenna, the kind used for cell coverage, it generates a wide transmission area, a main lobe. That's your wide flashlight beam. The power drops off pretty quickly, but you have to respect the exclusion zone right in front of it.
But the microwave dishes are the laser pointers.
Exactly. They're a narrow, highly concentrated, high-energy beam. They're designed for tight directional focus to link two sites miles apart. And crossing that beam at close range can instantly fry your drone's electronics. Instant loss of control.
So given that, how do pros manage the risk without just guessing?
The standard is the no-guess rule. It's all governed by regulatory guidance like Canada's Safety Code 6 or the FCC's OET Bulletin 65, and the U.S. pros never assume. They have to verify the site's specific RF safety plan, or they require the tower owner to reduce power or even shut down certain antennas for a specific window of time.
And the highest risk zone is?
Directly in front of the panel antennas or catastrophically crossing the beam of a microwave dish. You treat those as no-fly zones until you have confirmation that the power is off or reduced.
And if you don't respect those zones, the effect on the drone is immediate.
Oh, it's severe. The combination of high RF and all that steel creates major tower physics problems. The sources list three main effects.
Okay, what are they?
First is link degradation. High RF energy floods the drone's operating frequencies. Your video feed starts to stutter, your command latency increases, the delay between your stick input and the drone's response gets really unpredictable.
Okay, that sounds bad. What's second?
Compass anomalies. The huge steel structure acts like a giant unstable magnet. It just confuses the drone's sensitive compass. You get sudden, unexplained yawing or drift. Precise control becomes impossible.
And the third one, the most complex, GNSS multipath and shading. Can you break down multipath for us?
Sure. Think of it this way. Your drone needs to get signals directly from satellites to know where it is. But the steel tower acts like a giant mirror. So the drone gets the direct satellite signal, and a second, slightly delayed signal is bounced off the steel.
It's like a digital echo.
Exactly. It gets two versions of the signal, and it confuses its own position calculation. It thinks it's in two places at once. This causes what we call jitter or nervous flight. And on top of that, the tower can just physically block or shade the signals from half the satellites you need for a stable lock.
So it's flying blind, basically.
Or at least with very poor vision. Mastering RF mitigation is essential just to get stable data.
Now let's move to the other invisible hazard. Aviation regulation. This is the ultimate cross-border trap. What is perfectly legal in one country can be instantly illegal in another.
This needs deep focus because the legal rules determine if a mission is even possible. We have to look at the altitude rules, specifically contrasting the U.S. Part 107 rules with Canada's CAN-R 901.25.
Okay, so what does the U.S. rule allow that makes inspecting these super tall towers possible?
In the U.S., a pilot under Part 107 is normally capped at 400 feet above ground level, or AGL. But there's a critical exception. It allows them to go higher if they stay within a 400-foot radius of the structure and don't go more than 400 feet above the structure's highest point.
So if the tower is 1,000 feet tall, you can legally inspect from 600 feet up to 1,400 feet.
Precisely. The analogy holds. You can ride the tower upward like an elevator as long as you stay close. This rule is the key legal tool for high-altitude inspection in the U.S.
But Canada's rule is much stricter. That's the trap.
It's a major headache for international operators. In Canada, the general cap is 400 feet AGL, period. There's an exception, but it only lets you fly up to 100 feet above a structure. So for a 700-foot tower, a pilot in Canada is legally stuck at 500 feet total altitude without special permission.
So a legal mission plan for a tall tower in the U.S. is completely illegal in Canada.
Without special authorization, yes. To fly higher in Canada, you have to apply for a Special Flight Operations Certificate, or an SFOC. It's an intensive administrative process. It requires detailed risk plans, specific coordinates, and it can take weeks to get approved.
It's a much higher regulatory burden.
It is. And it forces pilots who work on both sides of the border to have two completely separate mission mindsets for the exact same type of job.
And that's before you even get to the physical safety of the flight. Which brings us to fail-safes and the #1 silent killer.
Guy wires.
Thin, under immense tension, practically invisible.
They are the ultimate environmental hazard. And this is where the default return to home, or RTH, feature on most drones becomes a huge trap near a guide tower. Novice pilots set their RTH altitude high, thinking it's safer to fly above everything, but near a guide tower, a high vertical RTH is a guy wire magnet.
Because the guy wires aren't vertical, they slope outward in wide planes.
Exactly. If the drone loses its link and just climbs straight up to its preset RTH altitude, it often flies right into the plane of the guy wires. Catastrophic failure.
So RTH can't just be a height, it has to be a route.
That is the core rule. The flight plan has to ensure the drone will never cross between guy wires under any circumstance. The pilot has to pre-visualize the RTH path, making sure it retreats laterally to the safe box through a safe corridor, avoiding those wire planes entirely.
And finally, there's the professional integrity piece, which is really a legal mandate. You can't just push through if things get unstable.
No. If a pilot continues a flight when the link is bad or the drone is jittery or the compass is glitching, they are rapidly escalating into what the regulations call careless, reckless, or negligent operation.
Which is illegal in both the US and Canada.
Absolutely. The moment control degrades, the professional action is simple. Retreat to the safe box, stabilize, and figure out what's wrong. Pushing through is not only reckless, it's illegal. You could lose your license.
Okay, so let's shift from just flying safely to capturing effective data. Flying safely gets you home. Mastery is about the quality and utility of the evidence you deliver. This is the mastery mindset.
We're moving from the pilot seat to the engineer's desk. We're focused on the four main outcomes the client is paying for: structural safety, system reliability, compliance and risk, and finally, actionable work packs, what needs to be fixed.
Let's start with structural integrity. What are the common defects the drone is hunting for?
The focus is on finding degradation. So we're looking for corrosion at hotspots, joints, connection plates, the base plates. We're also looking for obvious physical failures. Loose or missing bolts, warped hardware, bent or cracked steel members.
And you mentioned the visual clue of rust streaks.
A rust streak is a huge indicator. If you see rust coming down a tower leg, the source of that corrosion is almost certainly higher up. The pilot's job is to trace that streak upward to find the originating defect, which is often a missing bolt or a connection failure you might otherwise miss.
Moving on to the equipment, the cable management details seem like surprisingly high-value items.
They're crucial for system reliability. A failure here can be very expensive. We're looking for loose or missing hangers that let coax or fiber cables sag. Sagging leads to abrasion, where the cable rubs against the steel, and failures in the weatherproofing.
Like peeling tape or cracked connector boots.
Exactly. And the absence of a drip loop.
What's a drip loop and why is it so critical?
A drip loop is just a gentle curve in the cable right before it enters the connection box. Its whole purpose is to force water running down the cable to drip off the bottom of the loop instead of running right into the connection.
Ah, okay.
Without that loop, water funnels straight into the connection point. Water ingress into high-performance coax or fiber means signal loss and potentially replacing an entire, very expensive cable run.
And for a guide tower, the focus shifts to the anchor system.
Yes, the focus there is on the tensioned anchor points. We're looking for corrosion on the turnbuckles and clamps, cracks in the concrete anchors, signs of the earth shifting, or even frayed strands on the guy wire itself. A failure at one anchor can cause the whole tower to collapse.
And finally, the main event, the antennas themselves.
Here you have to meticulously document the mount integrity loose clamps, cracked brackets. For the antennas, you look for physical damage to the radome, the protective housing. And for microwave dishes, you're looking for clues that they've moved, like bent brackets or fresh scrape marks on the bolts where they've shifted under stress.
To make sure nothing gets missed, the sources outline a structured approach, the 5-flight recipe.
This recipe is the core of mastery. It turns a massive, complex task into 5 manageable, focused flights.
What's number 1?
1, the context orbit. This is a wide orbit, maybe 30 to 50 meters out. You're establishing the tower ID, the site context, and looking for major hazards or unauthorized attachments.
Okay, step 2.
2, the mid-level structure scan. This is a slower, closer orbit, focusing just on the steel itself. You're hunting for loose bolts and tracing those corrosion streaks.
3 is the antenna cluster.
Yes, the antenna cluster scan. This is the highest detail work. You approach each antenna sector and document the mount using clock phase shots, a front oblique, a side profile, and a rear quarter shot of every single antenna.
Number 4.
4, the cable run scan. This is a slow vertical ladder scan top to bottom. The camera is focused just on the cable trays, checking hangers, looking for chafe points, and verifying weatherproofing.
And finally, the base.
5, the base and foundation scan. Low-altitude passes, looking at anchor bolts, concrete cracks, security fencing. This systematic approach just guarantees you cover everything.
And that recipe is only useful if the evidence is definitive. If an engineer can't make a decision based on the photo, the flight was wasted.
Precision is everything. This is where the three-shot rule is mandatory. For every single defect, you capture 3 specific shots.
Wide, medium, and tight.
Exactly. Wide shows where it is on the tower, the context. Medium shows the specific component that has the issue, and tight shows the defect clearly. How bad is it?
And we established that the angle you shoot from matters more than just zoom.
Absolutely. A professional pilot has to prioritize oblique angles, 30 to 60 degrees. Flat-on shots hide texture and depth. Oblique angles use shadows and light to reveal the texture of rust, the depth of a crack, subtle deformation. You have to fly slower than you think to make sure those stills are sharp.
Finally, the reporting itself requires integrity. The pilot can't pretend to be an engineer.
It's the don't overclaim rule. You never say the dish is misaligned. You don't know that for sure. Instead, you use defensible observational language. Something like mount deformation observed. Recommend technician alignment verification. It protects your liability and gives the client an actionable recommendation.
And that recommendation gets a severity rating.
Yes, a clear 4-tiered standard so the client knows where to put their money. It ranges from urgent imminent failure or falling object risk
Something that needs immediate attention.
to high, which is clear degradation that needs repair soon.
Yeah.
Then monitor for early stage issues you need to track. And finally, cosmetic, minor stuff. This discipline is what turns raw data into a real capital expenditure plan.
So what does this all really mean? We've seen that professional drone tower inspection is this demanding convergence of 3 things: highly automated tech, strict regulatory and safety adherence, especially with RF and altitude rules, and incredibly precise inspection discipline.
The shift in value is just profound. It's not just about avoiding the risk of a human climbing anymore. It's about providing actionable, measurable 3D data. This lets tower owners manage their assets predictively, plan repairs, and even generate new revenue by using that digital twin for leasing.
We spent a lot of time on that critical difference between the U.S. Part 107 rule, which lets you ride the tower upward, and the Canadian rule, which imposes that much harder 400-foot ceiling without a ton of paperwork.
And that leads us right to our final provocative thought for you, the listener. That regulatory difference forces professional pilots to maintain 2 completely separate, conflicting mission mindsets for the exact same job.
One relies on a specific altitude exception, the other requires weeks of advanced approval.
So if a cross-border assumptions about something as simple as maximum altitude can be a common failure point, even for experts in a field dysregulated, what other deeply ingrained legal, procedural, or technical assumptions are you making in your own industry, in your own work?
Because that gap between what you assume is okay and what is actually required, that's where high-stakes operations, whether they involve drones or not, can fail.
And that's what can put you and your organization into reckless territory without you ever even realizing it. Something to chew on as you review your next big project.
That's a wrap on today's mission, Commander. See above, go beyond, get ahead. For more training, tools, and intel, head to skycommander.ca. If you learned something new, share it, subscribe, and leave us a 5-star debrief.